Hi everyone, I'm Bowen Liu, a PhD student at Department of X, University of Michigan. I'm very glad to present our work on Mmvc learned multimode video compression with block-based prediction mode selection and density adaptive entropy coding. In this paper, we will investigate a learning-based multimode video compression scheme, which adapts to different motion and contextual patterns in a unit of block. This framework applied a blockwise channel removal scheme to improve the sparsity under similar reconstruction quality. We implemented a density adaptive entropy coding scheme to encode dense and sparse residual blocks separately. Regarding the performance of our work, the proposed codec has achieved a performance superior or comparable to existing approaches on the commonly used benchmarking datasets. We also used the ablation study to demonstrate the effectiveness of adopting multiple mode prediction and compression scheme for various scenarios. We need video compression in our daily life to reduce the storage requirement, to allow faster transmission over networks, to improve the streaming user experience. And as a result, the goal of video compression is to minimize the file size while maintaining acceptable video quality, and also balance the trade-off between the video quality and bitrate rate. So the question is how to compress the video. We need to remove the redundancies in the video sequence. There are two major sources of redundancy. Spatial redundancy can be reduced by removing redundant information within a single frame, which has been well studied in the image compression field. And temporal redundancy can be reduced by exploiting similarity between consecutive frames. In video codecs, prediction helps to temporarily decorrelate the stored information so as to reduce the code size under a certain quality. I want to talk about some of the existing video compression methods. First are the standard codecs, such as AVC, HEVC, VVC, and so on. The rest are learning-based video compression algorithms proposed in recent years, like DVC, DCVC, RLVC, and VCT are some of the examples. The standard codec typically addresses various types of motion and content in a unit of microblocks, which is rarely seen in learning-based method. We wonder if a learning-based codec can get the best of both worlds. Thus, we propose a learning-based blockwise video compression scheme by applying the content-driven mode selection on the fly. Our scheme contains 4 prediction modes. One is skip mode. This mode aims to find the most condensed representation to transmit unchanged blocks. This mode is particularly useful for static scenes, where the same background is captured by a fixed-view camera. Another is a feature prediction mode. This mode is designed for the generic cases in the video sequence. And the feature propagation mode is also included. This mode is applied to some change blocks where no better prediction mode is available. This mode copies the previously reconstructed feature block as the predicted result. The last one is optical flow condition feature prediction mode. The OFC mode leverages the temporal locality of motions. The frame warped with object flow information is treated as a preliminary prediction of the current frame, providing guidance to this prediction model. The overall workflow is presented in this slide. The compression pipeline goes as mapping to feature representation, multimode prediction, channel removal, and density adaptive entropy coding. Here, I will go into our system step by step with details. The first step is the acquisition of feature representation. Each frame of the video sequence is first individually compressed to an optimal feature representation. The second step is feature domain video prediction. The proposed multimode prediction framework selects the best prediction for each block with the smallest entropy coded residue. Then the next step is channel removal. The adaptive residual channel removal guarantees the reconstruction quality while reducing the number of bits consumed by unimportant residual feature channels. The last step is applying the density adaptive entropy coding scheme to further reduce the bit rate. The adaptive entropy coding encodes the dense residual blocks and sparse residual blocks separately with different coding schemes. Then I want to present the visualization of our method compared with other standard codecs. As we can see from our construction on the left part, the details of the static background and dynamic objects are well preserved. Compared with HEVC and Mmvc with similar BPP, our result yields less block artifacts, preserving finer details. The complementary nature of different prediction modes in our scheme is visualized in this figure, which shows the decoded scene directly obtained from the predicted feature using a single mode or combined modes without residual compensation. Using FP mode only leads to a sharper details in general, but it loses some content such as the vocal behind the fountain and the rider's leg. On the contrary, applying OFC mode only results in unfaithful reconstruction near the horse's legs. By adopting multi-prediction mode that complement each other, our prediction is able to cover content variety in the original frame with a shorter bit string. To further demonstrate the benefit of a multi-mode prediction, we did an amplification study of various mode utilization. The quality is preserved with a lower bit rate when using the ensemble of FP and OFC modes compared to having either of them individually, indicating that two prediction modes can complement each other by capturing different motion. Including the feature propagation mode as an alternative prediction path further reduce the bit rate without degrading the quality. The compression ratio improves noticeably by introducing the skip mode as the final additional mode. The result collected from the connected dataset, where the scene are captured mostly by a fixed wheel camera, showcase the higher utilization of a skip mode brings a significant bit reduction. The last thing we want to talk about is the RD trade-off performance compared with other methods. Our method achieves state-of-the-art performance on benchmarking dataset. It can yield extremely high quality reconstructed frame in a relative high BPP range. Thank you for watching this video.